We looked at hydrogen and helium, diatomic molecules of them, looking at the 1s orbital and the 1s orbital being mathematically mixed to form the sigma 1s and the sigma star 1s. Now we're ready to run across that second period. In the second period, we know we have 2s orbitals and 2p orbitals for the atoms, and these 2s orbitals and these 2p orbitals will need to be mathematically interacting in the constructive and destructive interference in a similar way. They will once again form bonding and anti-bonding orbitals. So let's work our way through it. So we've got to mix the 2s orbitals and the 2p orbitals of the individual atoms. Okay? When the 2s's mix, it's very, very similar to when 1s's mix. They're just bigger. Okay? So we knew that when a 1s orbital and a 1s orbital mixed, we ended up making the sigma 1s and the sigma star 1s. Let's see if that all shows up. Yes, it does. This thing kind of was shaped like this, with the nuclei being engulfed in the space and the orbital surrounding that. And this was the orbitals, and they had a gap between the two, and that was the anti-bonding. Well, all we would have to do is replace the 1s with 2s, and it would look just the same. A 2s and a 2s from two different atoms that get mathematically mixed will form a sigma, but it's a sigma 2s, and it will look like this. And it'll form a sigma star 2s that will have that gap between them, with the electron signs, the signs of those two being opposite. We saw it as blue and red. Now, how are we going to mix the 2p's? What do we know about 2p orbitals? Well, let's just draw it out over here. In a 2p orbital, it's shaped like this. There's one along the x-axis, one along the y-axis, and one along the z-axis. So we have these three that are perpendicular to each other. This one is coming out and going into the plane of the board. And those guys can mix, and let's talk about how they do. All right, the mixing of p orbitals. Let's say in the two atoms, they have the p orbitals that are on the same axes pointing towards each other. If we were to take this orbital and mathematically mix it with this orbital, that is what's being represented in this image. It would form 2 go in and 2 come out. Now, when we look at this image, it's important for us to know where the nuclei are. Okay, so I'm going to kind of draw them big. The nucleus is in the middle of the p orbital. When we mix them in a constructive interference way, here are the nuclei, and we have a lot of electron density that is between those two nuclei. This is the bonding orbital. The anti-bonding orbital, here are the nuclei, and they have a gap between them. That's the anti-bonding one. And once again, the bonding are low in energy and the anti-bonding are higher in energy. Now, those are the ones that are along the x-axis that are pointing towards each other. Now we've got the ones that are perpendicular, that are going to sideways overlap. So let's look at the PY. Here's the nucleus, and here's the nucleus. And they're going to be interacting in a way where they're along sideways overlap, okay? Now when they do this, here is the nucleus and here's the nucleus. The blue area forms a lobe above and a lobe below the plane. And that is what we call a pi bond. Now, we talked about pi orbitals when we did valence bond theory, and we know that it had an electron density above and below the plane. We're seeing that happening here as well. The anti-bonding have a gap. Okay, that's the destructive interference. We still have electron density above the plane and below the plane, so it's still a pi bond. That's what we call it. But it has that star there because it's anti-bonding. Now, the ones in the y-axis and the ones in the z-axis are interacting in a very similar way. The z-axis, okay, coming in and out of the plane of my screen here. We've got the nuclei here in the middle. They are interacting this way, and we have the bonding and the anti-bonding, and the anti-bonding has the gap because we again have electron density that are on either side of that. It's this guy right here, but turned on its side. Okay, it's the exact same thing, bonding and anti-bonding. So these are how all the p orbitals can interact. So I'm going to try to draw these out overlapping each other so we can get an idea of happening on the screen just to give you another perspective of it. We know that there are 3 p orbitals. We know that one of those p orbitals are along the the x-axis. I'm going to call that one the x-axis, okay? We know that one is along the y-axis, so I'm going to call this one, let's see, I'm going to call this one my y-axis, okay? Up and down. So there is a p orbital along the y-axis, and then I've got the one along the z-axis, and we're going to say that the z-axis is coming in and out of the plane that this board is on, okay? So my z is going back here behind there like that. So I've got that, and I've got another, so that's in one atom. And in the other atom, it has these same 3 p orbitals. So I've got one in that axis, okay? I've got one in this axis, and then I've got one in this axis, okay? So I have those. Now we're going to focus in on the green. The way the green interacts is very different than the other 2. So I'm just with the green. The way the green interacts is to do kind of what we call a head-on mixing. So this and this. Now we saw this when we were doing valence bond theory, and we mixed those, we allowed them to overlap. Now what we're going to do is allow that idea to be they're mathematically mixing, not just overlapping. When they mathematically mix, they form two orbitals, one from constructive interference and one from destructive. The constructive one looks like this. It's got a big fat space and 2 little lobes, and that is the pi, and it gets a subscript. What would the subscript be? Well, these are the interaction of the 2 p orbitals, and which 2 p orbitals? They're the x 2 p orbitals. And then we would have them mathematically mixing in a destructive interference pattern, and we see that as, okay, here is a nucleus. There's a nucleus. Get them in the right same place. Here are my nuclei. They're in the same place. But we have a shape that kind of looks like this. Okay, this is an orbital. This is an orbital. It kind of looks like 2 orbitals, but this is an orbital. This is an orbital. This orbital is called pi 2p x with a star above it. Okay, so we have got these 2 new orbitals that came from these 2 old atomic orbitals when they interacted. One is lower in energy and one is higher in energy. Then we've got the blue. Now let's do the pink, because the pink will be easier. They're really easy to see. So we've got the p interacting with the p when they're along the same axis, okay, with each other. And we are going to, when they interact in a constructive interference way, we have these 2 bottom lobes forming a space, these 2 top lobes forming a space. The nuclei are in between them, and that is the constructive interference pattern, okay? And above that in energy, this is lower in energy, above that in energy would be when these 2 things are destructive interference, and it's kind of like, let me draw those 2 things. This would be higher in energy, I just don't have space to draw that, where they're kind of shying away from each other. This right here, okay, has a gap between the 2 nuclei. This one is called a pi 2p. It does not have a star because it's got this electron density above and below the plane and no gap in between. These are along the axes of the y-axis. This is my py, so I would call it pi 2py. And this would be the pi 2py, and it's got the anti-bonding. This would be above and below the energy. Now the blue form the exact same way as this, only it's turned on their side. So we've got the one out of the plane and back behind the plane, towards you and back behind you, interacting with each other. Then we're going to have electron density back here, and then one back behind it with the nuclei here, okay? So it's coming out at you and going back behind you. Same thing with this, coming out at you, going back behind there. Coming out at you, going back behind there. There are the 2 nuclei and a gap in between them. Okay, so those are all taking these guys, allowing them to interact in a way that they can, allowing them to mathematically mix as constructive and destructive interference. Now that's the theory. That is the theory behind all of this. Now let's look at the diagram and how their energies lie. Okay? This image here that we see on the screen is the way the 2 P's and the 2 S's interact. The bottom half of the screen are the sigma 2 S's, giving me the bonding and anti-bonding orbitals. So I'll come over here and remember, This guy looks like this. This guy kind of has a gap between them, okay? Where we've got a gap between them. Those are the two molecular orbitals formed by these two atomic orbitals, this guy, and they quit existing when these are formed. Then we got our two P's, okay? We got our PX, our PY, and our PZ. Our PX, our PY, and our PZ. When the PX's interact, they give us the sigma 2P and the sigma star 2P, and it no longer exists. When the PYs and the PZs, they're forming the pi's. Now see these two orbitals down there and these two orbitals up here? 4 went in, 4 came out. What you need to know is this orbital, this order. When you're dealing with the second period, and you're talking about MO theory, we know that the atomic orbitals cease to exist, they no longer exist, and now all of these exist instead. And you have to be able to name them from lowest energy to highest energy. Now, I kind of think of this as a shape. Let me erase and let me show you what I mean by a shape to help me keep it straight. All right, you're going to think this is silly probably, but if it helps you remember it, who cares? All right, it's a Christmas tree. Boom, 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 boom. Okay, here's my Christmas tree. I've got 1 and 1. That's this one and this one. I've got wide and skinny and wide and skinny. That's my shape, right? These are my sigmas. This is my pi. This is my sigma. Okay, this is pi, this is sigma. These are from the 2s orbitals. There's a sigma and a sigma star. These are from the 2p orbitals. There's a pi and a pi star. These are from the 2p orbitals. There's a sigma and a sigma star. So I go dun dun, then 2 and n and 2 and n. That's my visual image for me. But you have to come up with your own visual image. Now what's the difference between those on the left and these on the right? The first boron, carbon, nitrogen, and actually the ones before that, what would that be? That'd be lithium and magnesium, diatomic, dilithium, there you go. They would follow this arrangement, and then the bigger elements, oxygen, fluorine, and nitrogen, follow this. And where is it different? It's different right here. Those two are flipped. The reality is, if you were asked to do a molecular orbital diagram and get information from it, you can use this one every time. The reality is those two are flipped, but they're far enough down in your molecular orbital diagram that it will not make a difference. So what we're going to do is we're going to practice doing a bunch of these, and we'll keep staying on the computer screen here and work on these one at a time. So we know that the rules for doing molecular orbital configurations is the same as if you were doing them for atomic orbitals. Hund's rule, Aufbau principle, Pauli exclusion principle, all of those happen. So here they are. You go from lowest energy to highest energy, only 2 electrons per orbital. If they're degenerate, remember what that means? They have the same energy, then you half fill before you go back and fill. That was Hund's rule. We're following all the rules that we knew of before. Now here's one thing that is going to help simplify how much we have to do. We're only going to consider valence electrons, okay? So when we're filling in these orbitals, we're going to forget about the inner shell. The inner shell will be the 1s orbitals mixing to form sigma 1s and sigma star 1s. We won't worry about those. We'll just go to our final image and only count valence electrons, okay? Only do those valence ones. So I've got my Christmas tree. All right, that's what's here. Boom, 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 boom. All right, I got that right there. This is the part that I'm interested in. I don't care about these because they don't longer exist. And so if I were sitting down and having to do this from scratch, what I would do is say, okay, I've got sigma 2s, sigma star 2s. I'm just constructing this out. Then I know I have my pi's and then my sigmas and then my pi's and then my sigmas. These are the pi 2p's, the sigma 2p, the pi, I know it's pi because it's the one with 2p star, and the sigma 2p star. That's what I would have to construct. But it's already drawn on this image for me. Now I'm ready to, can do it for any I can use this order for anything that I give to you. So let's see about these dilithium crystals that they always talk about in Star Trek. Can you form a bond according to molecular orbital theory for this? Well, we need to go to a periodic table, and you might want to grab one and pull it over, and I want you to count valence electrons, because this is an orbital diagram for only the valence electrons. Each lithium has 1 electron in its valence shell, all right? So we multiply by 2, and I have 2 electrons to work with lithium. So I come over to my diagram and I'm ready to put those in. I put 1 electron there, and there's room for a 2nd electron, and I'm done. That would be the molecular orbital diagram for Li2. If I said, well, what is the orbital diagram? I mean the electron configuration. When I draw the arrows, that's called the orbital diagram when I do what you see there. But if it says what's the electron configuration, then we just write what we see here, which we have a sigma 2s, and we tell how many electrons are in it, so that would be the electron configuration of it. Now once you do that, that might be one level of question. The next level of question is, well, can you tell me about this molecule? Can you calculate the bond order? All right, so bond order would be electrons that are in bonding orbitals. Those are the ones without circles, okay? So I have 2 electrons in bonding orbitals. I count up the number of electrons in anti-bonding, which there aren't any, and then I divide by 2. And so we would say, yeah, we can have dilithium, and it would be a diatomic molecule with a single bond between them. We could also ask the question, is this molecule paramagnetic or diamagnetic? Well, if you've got orbitals that are paired, okay, the electrons are paired, that's not paramagnetic, that's diamagnetic. Remember, para comes from parallel. That means you have electrons that are not paired up. So we have 2 electrons, that's diamagnetic, and that's the kind of things you can answer with our molecular orbital theory. What kind of bonds are between the atoms or an ion, and then what kind of, is it paramagnetic or is it diamagnetic? Let's do another one. B2. All right, so you find boron on the periodic table, and you see that boron has 3 valence electrons. With its 3 valence electrons, there's 2 borons, so we have 6 to work with. We come over to our orbital diagram and we're working our way up the middle because these no longer exist. They have been mathematically mixed to form what we see up through the middle. We have 6 electrons to put in. So we do 1, 2, 3, 4. Ready to go to the next level, and notice these are degenerate. They have the same energy. What do? We do Hund's rule. We half fill, 5, 6. Okay, so there we have the orbital diagram drawn out. Electron configuration for the valence electrons only is sigma 2s with 2 electrons, sigma star 2s with 2 electrons. And then what we do here, we say, well, it's pi 2p, and it has 2 electrons. It doesn't show me very well that they're spread out like they are. We know they are spread out. They are 1 in each orbital. This doesn't show me that as well, but as long as I always know that a pi, every time we have a pi, there's 2 orbitals that are equal in energy, then it will work for me. And then we can answer those questions, okay? So we would calculate the bond order. Bond order would be, well, we count up the number of electrons in bonding orbitals. There's 1, 2 here, and this doesn't have a star, so there's 2 more there. That would be 4, minus the anti-bonding, which is right here. There's 2 there. 4 minus 2 divided by 2 would give me a bond order of 1. So this would have, again, a single bond between the borons. But in this one, would it be diamagnetic or would it be paramagnetic? Well, it'd be paramagnetic because we have these parallel spins. Paramagnetic, and what would that mean in terms of a magnet? It means it would be attracted to a magnet as opposed to diamagnetic. Now you get to work one, okay? So I want to stop and you're going to ask you a question about this. What is a bond order? Before I let you go with that, remember, this is only the valence electrons. So you only count up valence electrons for the 2 oxygen atoms and place them in there and then get a bond order. Well, you by now know it's a bond order of 2. We had 6 valence electrons, that's 12 total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that is what we have here. Now, if we had incorrectly put these in a different order there, if we had incorrectly put that these 4 are below and these 2 are up, would it change our bond order? No, we would still have 2 electrons in the sigma 2p, and we would still have 4 electrons in the pi 2p, so that would not affect the answer to this question. Okay, so we can still do the 2, 1, 2, 1 and answer the question correctly. Now we could also ask the question about whether this is paramagnetic I'll come back to that. We could also ask the question, is this paramagnetic or is this diamagnetic? Well, you look at it, what do you see? We see these 2 unpaired electrons that tells me it's paramagnetic. Now there are going to be times that you're going to do some comparisons, and let's just do another one. Let's do a peroxide ion, O2 2 minus, okay? And we'll just do it here on this screen. O2 2 minus. How many electrons do we have? Well, we know that oxygen has 6. Both oxygens together is 12, and then we'll add 2 more for that -2 charge, and I have 14 electrons to work with. So I start down here and do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So is this one paramagnetic or diamagnetic? Well, this one would be paramagnetic. And let's count the bond order, okay? The bond order, we're going to do bonding electrons. I will circle the bonding. 2, 4, 6, 8. We have 8 bonding. I'll put a square around the anti-bonding. 2, 4, 6. And then I'll divide by 2, and that'll give me a bond order of 1. So on O2 without the charge, it had a bond order of -2. O2 with the charge of 2 minus, that's a peroxide, it has a bond order of 1. Sometimes you might be asked a question about which is more stable. And so if we were going to compare our oxygen, O2, which had a bond order of 2, with O2 2 minus, which had a bond order of 1. If the question says which one is more stable, you would look at the bond order. The bigger the bond order, the more sharing we thought of as it before, but that is more, now we're thinking about it, well, we got more electrons in bonding orbitals than we do anti-bonding orbitals, and we have the bottom line is the more bonding orbitals you have, the stronger your bond is. The more anti-bonding you have, the weaker it is. So the bigger the bond order, the stronger, or the more stable, I should say, the more stable the compound. Okay, we've already answered that question. It is paramagnetic. Now, I told you at the beginning that molecular orbital theory was important because in valence bond theory, we could not account for the behavior of O2. We noticed that oxygen, when you liquefy it and pour it through a magnet, would be attracted to that magnet, so we knew it had to be paramagnetic. Valence bond theory showed everything paired up. Finally, we see a theory now that shows us that this guy is not got everything paired up. We have, again, the look of it, which we have in our notes already, that looked like this, okay? Those unpaired electrons there let us know that it is going to be attracted to a magnet. We've already done that one. And let's do this one. F2 plus. So fluorine has 7 valence electrons. Each fluorine is 7. We're only doing valence. And then we subtract 1 for the positive charge. So that's 13 electrons to work with. We start down at the bottom. We're doing the ground state. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13. So there would be the orbital diagram. You could take it and do the electron configuration where you're writing with a superscript to tell you how many electrons are in each. And let's have you calculate the bond order. All right, let's see, what did you come up with? I haven't done this one, so I'll do this one with you. You've already checked yours out. The number of electrons that are in bonding orbitals are 2, 4, 6, 8. Anti-bonding are 2, 4, 5, okay, divided by 2. So that's 3 divided by 2, or 1.5. So you can have bond orders that are fractions. Is this one paramagnetic or diamagnetic? Well, there it is. That unpaired electron tells me it's paramagnetic. So molecular orbital theory, we will keep it simple. Now this seems, it's pretty, it's a lot of theory, okay? It's heavily theory laden, and a lot of times students are like, what's going on? So you might have to watch this video more than once. But what I need you to understand about it is that it is taking atomic orbitals across the molecule, allowing them to mix to form new orbitals that we've never seen before. We call these orbitals molecular orbitals. Every orbital that comes into the mix will form an equivalent exact number of that orbitals coming out, okay? So when 2 orbitals come in, 2 orbitals come out. When 2 orbitals come in, 2 orbitals come out. So the number of orbitals that you had that were atomic orbitals is how many molecular orbitals. And it is orbitals over the entire molecule. We're keeping it simple here by only having 2 atoms, never more, when we're having to go actually come up with the molecular orbital diagram. You get more than 2 atoms, it can get a little bit more complex. We're also making it simple by keeping the 2 atoms that are mixing being the same atom. Because if you bring in a 2p orbital from fluorine and you bring in a 2p orbital from oxygen, they have different energies. And when they mix, different things happen. So we won't have what we call heteronuclear diatomic molecules. They will be homonuclear of the same atoms, keeping it simpler, okay? And the types of things that you can determine from molecular orbital theory are how many bonds does it have? That's the bond order. And is it paramagnetic or diamagnetic? And then you can compare atoms to their ions and establish which one is more stable. And it's more stable if it has a bigger bond order.